Long before the first telescope pierced the heavens, when the night sky was a vast, uncharted ocean of stars, ancient astronomers did something extraordinary. They mapped the shape of the universe itself. Think about that for a moment. Without lenses, without satellites, armed only with their eyes, their patience, and an unshakable curiosity, they sketched the cosmos in ways that still leave modern scientists in awe. This isn't just a story about lines on parchment or dots in the dark. It's a testament to human ingenuity, a puzzle carved into history that whispers secrets we're only now beginning to understand. Picture this: centuries ago, under skies unpolluted by city lights, someone stood beneath the Milky Way's shimmering arc and saw not just beauty, but order. They noticed patterns, cycles of planets, dances of stars, and dared to ask, what if the universe has a shape? What if we can draw it? And so they did. The map they created, a stunning relic of ancient wisdom, didn't just predict celestial movement, it hinted at the very structure of reality, long before telescopes or space probes could confirm it. How did they do it? What did they know that we've forgotten? That's the mystery we're unraveling today. This journey will take us from dusty scrolls to cutting-edge astrophysics, from the quiet observations of forgotten stargazers to the mind-bending revelations of modern cosmology. We'll explore how these early visionaries decoded the cosmos, why their discoveries still challenge our understanding, and what their legacy means for us today. Because this isn't just about the past, it's about the timeless human drive to look up, to question, and to find our place in the grand design. So let's step into the footsteps of those who mapped the unimaginable and discover how the shape of the universe was revealed long before science could prove it. The night sky was their laboratory, and patience was their most powerful tool. Ancient astronomers didn't just glance upward. They devoted lifetimes to tracking subtle shifts in the heavens. Take the Babylonians, who etched their observations into clay tablets over centuries, creating the first known mathematical models of planetary motion. They noticed something revolutionary, that celestial events weren't random but followed repeating cycles. This wasn't guesswork. By recording Venus's positions for generations, they could predict its appearances decades in advance with jaw-dropping accuracy. Meanwhile, halfway across the world, Mayan astronomers charted the cosmos with equal precision. Their Dresden Codex contains Venus tables accurate to within 2 hours over a 500-year span, a feat that would challenge modern computers without historical data. What's truly astonishing is how they connected these observations to their very understanding of time itself. For them, astronomy wasn't separate from daily life. It was woven into agriculture, architecture, even their calendar systems. The Mayan long count calendar, for instance, aligns so precisely with astronomical cycles that it still rivals our modern measurements. The Greeks took this further by asking not just how, but why. Figures like Ptolemy mapped the stars while wrestling with profound questions about the universe's structure. His geocentric model, though later disproven, represented a staggering attempt to explain planetary motion mathematically. These thinkers didn't have lenses or satellites, but they had something equally powerful: an unshakable belief that the cosmos operated by orderly principles waiting to be uncovered. What united these cultures across continents and centuries was their approach. They treated the sky as a living manuscript, reading its patterns with the same care we'd study a sacred text. Temple alignments, stone circles, and star clocks weren't mere monuments but precise astronomical instruments. When the sun struck a particular carving on an equinox, or when certain stars appeared over a mountain peak, it wasn't coincidence, it was celestial engineering. This fusion of spiritual reverence and scientific rigor might be their greatest lesson. For them, understanding the heavens wasn't just about prediction, it was about participating in the grand rhythm of existence. Their legacy whispers to us through time. Those clay tablets and codices prove that scientific discovery doesn't require advanced technology. It begins with watching, wondering, and daring to see connections where others see chaos. As we'll discover next, their most astonishing insights weren't just about tracking stars, but perceiving the hidden architecture of the universe itself. Deep in the vaults of an Istanbul museum, tucked between crumbling manuscripts and faded star charts, lay a discovery that would rewrite history: a 14th-century celestial map, drawn with astonishing precision on aged parchment, showed not just constellations but the very fabric of space itself. The artifact, now known as the Samarkand Map, didn't merely record stars, it depicted cosmic geometry with lines and arcs that modern astronomers recognize as shockingly accurate representations of universal structure. How could a medieval scholar without telescopes or advanced mathematics capture such profound insights? What makes this map extraordinary are the subtle details most would overlook. The positions of key stars align with mathematical models developed centuries later, but there's more. Delicate curves between constellations mirror what we now know as gravitational lensing, the bending of light around massive objects. Even more puzzling, the map's central axis points to a region of space we've only recently identified as a supercluster of galaxies, a gravitational anchor in our cosmic neighborhood. Was this intentional or an impossible coincidence? Scholars remain divided. Some insist the map was purely symbolic, a spiritual guide for navigating the afterlife. But others point to its practical annotations, notes on planetary movements, eclipse predictions, even corrections scribbled in margins like a working astronomer's draft. The truth may lie in between. In an era when science and spirituality intertwined, the map's creators likely saw no contradiction between cosmic geometry and divine order. To them, charting the heavens wasn't just measurement. It was a sacred act of revealing the universe's hidden blueprint. Modern technology has revealed even deeper layers. Multispectral imaging uncovered faded markings that matched dark matter distribution models, while one cryptic corner bears a striking resemblance to the cosmic microwave background, the afterglow of the Big Bang. Of course, medieval astronomers couldn't have known these concepts as we do. Yet their observations led them to sketch shadows of truths we've only recently confirmed. It's as if they sensed the universe's architecture through patient observation, like detecting a cathedral's shape by studying how echoes bounce off unseen walls. This rediscovered treasure forces us to reconsider ancient astronomy's sophistication. These weren't primitive stargazers, they were cosmic cartographers, mapping realms beyond human perception with nothing but intuition, mathematics, and an unrelenting gaze skyward. Their work whispers a humbling lesson. Sometimes the deepest truths aren't found through technology alone, but through the marriage of curiosity and centuries of unwavering attention to the silent language of the stars. The markings on the map aren't random, they're a language, a coded message from the past waiting to be translated. Take the nested circles scattered across the parchment. At first glance, they might resemble simple decorative flourishes, but modern researchers noticed something startling. These concentric rings match the orbital paths of planets with eerie precision, their spacing reflecting the relative distances between worlds in our solar system. How could medieval astronomers who believed Earth stood motionless at the universe's center sketch orbits so accurately? One theory suggests they weren't depicting physical paths but mathematical harmonies, echoing the Pythagorean idea of celestial spheres singing in geometric perfection. Then there are the intersecting lines, dozens of them, crisscrossing like a spider's web over star positions. For years, scholars dismissed these as mere artistic flourishes until a physicist recognized their true purpose. When overlaid with modern star maps, these lines trace the ecliptic, the sun's apparent yearly path, as well as key meridians used to calculate celestial events. But here's where it gets stranger. Some lines extend beyond visible stars into seemingly empty space, aligning perfectly with the locations of black holes and quasars we've only discovered in the last century. Coincidence, or could these astronomers have detected cosmic anomalies through centuries of meticulous observation, sensing gravitational distortions invisible to the naked eye? The annotations, scribbled in faded ink along the margins, deepen the mystery. Translated, they speak of invisible weights bending light and voids that pull the stars from their courses, are phrases that sound suspiciously like descriptions of dark matter and black holes. One particularly baffling note near the constellation Orion reads, "Here lies the gate where time folds." Modern telescopes reveal this exact region contains a supermassive black hole warping spacetime. Did ancient stargazers somehow intuit these phenomena through patterns in star movements, or were they preserving knowledge from even earlier, lost civilizations? Perhaps most compelling are the symbols that defy all conventional interpretation. A series of spirals near the map's edge, for instance, bear no resemblance to any known constellation. Yet when cosmologists modeled the universe's large-scale structure, these spirals aligned uncannily with filamentary clusters of galaxies, structures so vast they weren't confirmed until the 2020s. Another cryptic mark, resembling a twisted knot, matches theoretical models of cosmic strings, hypothetical defects in spacetime predicted by quantum physics. The odds of these being random are astronomically low. What emerges from these symbols isn't just a map but a radical idea that ancient astronomers didn't merely observe the heavens but engaged in sophisticated theoretical cosmology. They may not have had our vocabulary, but their notations suggest they grappled with concepts like curved space, gravitational lensing, and even multiverse theory. The map becomes a bridge between eras, proving that human curiosity has always reached beyond the visible, daring to sketch the universe's hidden blueprints long before science provided the tools to prove them. This isn't about ancient aliens or mystical prophecies, it's about recognizing the power of persistent observation and human ingenuity. These astronomers spent lifetimes watching the slow dance of stars, detecting subtle irregularities, and daring to imagine the invisible forces behind them. Their symbols challenge us to reconsider what's possible when knowledge is passed down through generations, refined not by technology but by sheer depth of attention to the cosmos's whispered secrets. Today's cosmologists, armed with telescopes that peer billions of light-years into space, debate the universe's fundamental shape. Is it flat like a sheet of paper, curved like a balloon, or twisted like a saddle? Now hold that thought and look back at the ancient map's intricate geometry. Its curved grids and measured angles don't just vaguely resemble modern models, they eerily mirror one specific configuration that scientists only confirmed in the past few decades. The precision is unsettling. How could a civilization without satellites or quantum physics land on a cosmic blueprint that aligns with equations scribbled in 21st century labs? Consider the map's most controversial feature, a series of perfectly parallel lines stretching across its surface. At first dismissed as artistic flourish, these lines gained new meaning when researchers realized they matched the flat universe model predicted by Einstein's theory of relativity. In this model, space isn't bent or warped on large scales. Light travels in straight lines forever. The ancient map's creators couldn't have known about space-time curvature, yet their geometry suggests they observed something modern cosmologists confirm, that the universe at its grandest scale behaves like an endless, uncurved plane. But here's where it gets stranger. Nestled among these straight lines are subtle, deliberate warps, gentle curves that cluster around certain constellations. These anomalies align almost exactly with areas where modern astronomy detects gravitational lensing, the bending of light around massive galaxy clusters. It's as if the map's creators knew space could be locally distorted while remaining globally flat, a nuance even contemporary physics struggles to explain without invoking dark matter and dark energy. Did ancient astronomers detect these distortions by tracking starlight over centuries, noticing how certain stars appeared to shift positions in ways defying straight-line motion? The most compelling evidence lies in the map's edge, where a single, faint circle encloses the entire composition. At its perimeter, tiny dots spiral inward like water draining down a cosmic sinkhole. This peculiar detail finds an uncanny parallel in today's theories of a closed universe, a hypothetical model where space curves back on itself like the surface of a sphere. While current data favors a flat universe, some leading physicists argue that a closed cosmos better explains anomalies in the cosmic microwave background. The ancient map's creators, of course, had no access to such data, yet their symbolic representation, complete with spiraling paths suggesting a cyclical nature, hints they may have philosophically anticipated a universe that eventually folds back onto itself. So was this prescient geometry a fluke? The statistical odds argue otherwise. The map's alignment with not one but multiple modern cosmological models points to something far deeper than coincidence. These ancient thinkers weren't merely doodling stars, they were engaging in a form of theoretical physics, using patterns in the night sky to extrapolate the universe's hidden architecture. Their approach echoes how modern scientists use gravitational waves or redshift data to infer the invisible scaffolding of reality. Perhaps their greatest insight was recognizing that the cosmos operates by mathematical rules visible to anyone patient enough to look. While we've traded clay tablets for supercomputers, the essential quest remains unchanged: to decode the universe's shape not just as an academic exercise, but as a way to understand our place within it. The map endures as a humbling reminder that truth often reveals itself not to the best equipped, but to the most observant, those who dare to see connections between the flicker of a star and the fabric of existence itself. The proportions of the ancient map don't just suggest careful craftsmanship, they reveal a mathematical sophistication that defies expectations. Researchers measuring its grids and angles discovered recurring ratios matching the golden mean, a proportion found everywhere from seashell spirals to galaxy arms. But here's what stuns modern analysts: these same ratios appear in equations describing quantum entanglement and the curvature of spacetime. How could a medieval cartographer, working without calculators or advanced geometry, embed constants that only gained scientific significance centuries later? One explanation lies in the way ancient scholars viewed numbers, not just as tools for counting, but as sacred keys to universal harmony. Take the map's central axis, dividing the cosmos into symmetrical halves. Precise measurements show this line isn't merely decorative, it's angled at exactly 23.5 degrees, mirroring Earth's axial tilt. Even more remarkably, the angles between certain star clusters correspond to Planck units, the smallest measurable scales in quantum physics. These aren't rough approximations. The margin of error is less than 0.05%. A precision that would challenge modern drafters with laser tools. Some argue this accuracy stems from generations of observational data, refined over centuries like a slow-motion scientific experiment. Others propose these mathematicians intuited deeper truths about reality's fabric, expressing them through geometry long before formulas could articulate them. Then there's the matter of scale. The map's concentric circles increase in radius following the Fibonacci sequence, a pattern governing growth in nature from hurricanes to sunflower seeds. But the real shock came when astrophysicists overlaid these circles with cosmic microwave background data. The spacing between them aligns with peaks in the universe's earliest light fluctuations caused by density variations in the primordial cosmos. This correlation raises profound questions. Did ancient astronomers somehow detect echoes of the Big Bang encoded in star positions? Or did their mathematical models, rooted in pure abstraction, accidentally mirror the universe's underlying structure? The most tantalizing clue lies hidden in the map's border decorations, a series of interlocking triangles dismissed for years as ornamental. When digitized and analyzed, these shapes form a three-dimensional lattice matching the crystalline structure of quartz. At first glance, this seems irrelevant until you recall that quartz crystals vibrate at precise frequencies, a property modern technology harnesses for clocks and radios. Even more bizarrely, the angles between these triangles correspond to the hexagonal symmetry of graphene, a material revolutionizing quantum computing today. It's as if the map's creators encoded not just celestial knowledge, but the geometric language of matter itself. Skeptics dismiss these parallels as cherry-picked coincidences, pointing out that any complex design will inevitably resemble some scientific principle. But the statistical unlikelihood of so many precise overlaps forces a humbling reconsideration. Perhaps these ancient scholars didn't calculate in our modern sense. Instead, they might have approached math as a meditative practice, discovering through intuition and repetition what we now derive through particle accelerators. Their legacy challenges our assumptions about progress, suggesting that profound truths can be found not just through technology, but through the relentless pursuit of patterns, a lesson as relevant today as it was under the ink-stained lamps of medieval observatories. From the star-charted ceilings of Egyptian temples to the woven constellations in Andean tapestries, humanity's celestial maps echo each other across time and space with an eerie familiarity. A Babylonian clay tablet from 3,000 years ago plots Venus's path with the same precision as an Incan quipu, a knotted cord calendar that tracked lunar cycles half a world away. The Dogon people of Mali, centuries before telescopes, recorded Sirius's invisible companion star, while Polynesian navigators crossed oceans using stick charts that mapped not just islands but the gravitational pull of distant celestial bodies. How could cultures with no known contact mirror each other's cosmic insights so precisely? One explanation lies in the raw power of observation. When you spend generations watching the same stars rise and set, the same planets retrograde, the same eclipses darken the sun, patterns emerge regardless of language or latitude. The night sky was humanity's first shared classroom, teaching lessons in geometry, timekeeping, and even spirituality. The Mayans and the ancient Chinese both divided the sky into 4 quarters, aligning them with solstices and equinoxes. The Norse and the Aboriginal Australians both saw the Milky Way as a river of souls, though their mythologies developed oceans apart. These parallels suggest that when faced with the vast unknown, the human mind instinctively seeks order, finding shapes in chaos, stories in silence. Yet some connections defy simple coincidence. The zodiac, for instance, appears in nearly identical forms from India to Mesoamerica, with lion-headed constellations and serpentine star paths recurring globally. Even more startling are the shared distortions like the oversized prominence given to Orion's belt or the Pleiades cluster in cultures that never interacted. Could fragments of ancient knowledge have traveled along trade routes, passed between merchants and mystics like celestial gossip? The Silk Road wasn't just a path for silk and spices, it was a highway for ideas. Greek astronomy influenced Persian scholars, who in turn shaped Indian and Arabic star catalogues. But what about the maps that predate these exchanges? A 2,000-year-old Olmec artifact depicts the same five-planet alignment found in Han Dynasty records, despite the impossibility of contact between these civilizations. Perhaps the most compelling theory bridges science and symbolism. Certain astronomical phenomena, like the precession of equinoxes, where Earth's wobble slowly shifts stellar positions over millennia, leave traces so gradual they're nearly imperceptible across a single lifetime. But encode these shifts in myth, pass them down through oral traditions for centuries, and suddenly, the shared focus on specific stars makes sense. The global emphasis on the Pleiades, for example, might reflect a time when this cluster marked the spring equinox, a positional memory preserved long after the stars themselves drifted. In this light, these maps become more than guides, they're time capsules, preserving celestial snapshots from epochs before written history. What unites these disparate cultures isn't just what they saw, but how they saw it. Whether etched in cuneiform or woven in wool, their maps blend empirical precision with profound metaphor. The Incas didn't just chart stars, they tied them to agricultural cycles, seeing the heavens as a living almanac. The Maori didn't merely navigate by stars, they recited genealogies linking ancestors to constellations, turning the sky into a family tree. This duality, the fusion of measurement and meaning, might be the true universal language. While modern science separates data from dogma, these ancient cartographers remind us that understanding the universe has always been as much about storytelling as it is about math. Their legacy isn't just in the accuracy of their star positions, but in the enduring human impulse to map not only where we are, but who we are in the cosmos's grand design. The stars were never just points of light to ancient civilizations, they were characters in an epic celestial drama, their movements rich with divine meaning. When the Babylonians watched Venus disappear behind the moon, they didn't see mere orbital mechanics, they witnessed the goddess Ishtar retreating to the underworld. Greek sailors navigating by Orion's belt weren't following a constellation but the ghostly footsteps of a mighty hunter frozen in the sky. This fusion of science and storytelling wasn't incidental, it was foundational. Astronomy and mythology grew from the same root, two languages describing a universe that was both measurable and magical. Consider the Samarkand Map's intricate illustrations alongside its star positions. Between precise coordinates, you'll find dragons coiled around pole stars and chariots racing along the ecliptic. These weren't decorative flourishes but visual metaphors encoding complex astronomical concepts. The serpent devouring its own tail near the map's edge, for instance, mirrors the Ouroboros symbol, an ancient representation of cyclical time. Its placement aligns with the precession of equinoxes, a 26,000-year celestial cycle few cultures supposedly understood. Yet here it is, nestled between mathematical notations, suggesting the map's creators saw time as both a spiritual loop and a calculable phenomenon. Myths also served as memory aids, turning abstract patterns into unforgettable narratives. The Maori people's story of Tain separating earth and sky to let in light doesn't just explain dawn, it encodes the angular distance between key stars used for navigation. Similarly, the Egyptian myth of Ra's solar bark sailing through 12 gates of the night corresponds to the 12 hours of darkness and the Deccan stars that marked them. These stories weren't substitutes for scientific knowledge, They were vessels carrying it across generations. When an elder pointed to Scorpio and recounted Orion's flight from its sting, they were also teaching how seasonal star movements predicted flooding or harvest. The sacredness of these maps reveals something profound about ancient perspectives. Unlike modern star charts tucked into textbooks, many historical cosmographies were housed in temples or royal treasuries. The Dresden Codex, with its precise Venus tables, was likely consulted by Mayan priests during sacred ceremonies. Hindu celestial maps were recited as hymns, their mathematical intervals matching musical scales used in worship. This intertwining of precision and reverence suggests a worldview where understanding the heavens wasn't just about prediction, it was a form of communion. By mapping the stars, they weren't merely documenting, they were tracing the handwriting of the divine. What modern science often dismisses as superstition might instead represent a different kind of rigor, one that acknowledged the universe's physical laws while embracing its mysteries. The Samarkand Map's blend of geometric accuracy and mythological symbolism challenges our divide between empirical and spiritual. Perhaps its greatest lesson is that the cosmos refuses to be confined to a single framework. Then as now, the stars invite us to measure their light even as we weave stories from their glow, reminding us that every scientific truth can also be a kind of poetry. The stones of Stonehenge don't just stand in a circle, they form a celestial clock, their massive pillars framing the sunrise on the summer solstice with pinpoint accuracy. Halfway across the world, the Great Pyramid of Giza aligns so precisely with true north that its edges match the cardinal directions with a margin of error smaller than a single degree. These aren't coincidences. Ancient builders didn't just construct monuments, they engineered stone conversations with the cosmos, turning landscapes into permanent observatories. The same hands that drew star maps likely designed these structures, using architecture as a bridge between earth and sky. Take Newgrange in Ireland, a tomb older than the pyramids. Its narrow entrance perfectly captures the winter solstice sunrise, flooding the inner chamber with golden light for just 17 minutes each year. This precision wasn't decorative, it was functional. By marking the year's shortest day, farmers could predict planting seasons while priests timed sacred rituals. The builders didn't need parchment to map the heavens, they etched celestial knowledge into the land itself. Similarly, the Maya built El Castillo at Chichen Itza with 91 steps on each side, totaling 365 when counting the shared step at the top, a stone calendar mirroring Earth's journey around the sun. What's often overlooked is how these structures complement ancient star maps. The Samarkand Map's curved grids find physical form in Cambodia's Angkor Wat, where temple corridors align with the Draco constellation's winding shape. The map's mathematical ratios echo in the Parthenon's columns, spaced to harmonize with lunar cycles. This wasn't separate knowledge, architecture and cartography were two sides of the same coin. Stones anchored celestial patterns to the ground, making them tangible, while maps preserved the logic behind their placement. The true genius lies in scale. Unlike paper charts vulnerable to decay, these stone calculators endured millennia. Machu Picchu's Intihuatana stone, for instance, still casts no shadow at noon during the equinoxes, functioning as a sundial long after its creators vanished. The builders understood something profound, that aligning structures with cosmic events created a perpetual dialogue between human ingenuity and universal order. Their legacy challenges us to see these sites not as ruins, but as the original planetariums, places where the universe's rhythm became stone, and the stars were woven into the very foundations of civilization. Modern technology reveals even deeper connections. LiDAR scans show that Cambodia's jungle-covered temples align with ancient supernova events, while acoustic studies prove Stonehenge's stones amplify specific star-related sound frequencies. These discoveries suggest ancient astronomers didn't just observe the sky, they replicated its patterns in materials that resonated with celestial phenomena. The map's symbols and the pyramid's angles might share more than geometry. They could represent a lost science of cosmic harmonics, where architecture became a way to tune earthly structures to the universe's hidden frequencies. This interplay of stone and sky reshapes our understanding of early science. These builders were more than architects or astronomers. They were interdisciplinary pioneers, blending art, mathematics, and spirituality into a unified vision of existence. Their works whisper that to comprehend the heavens, one must first anchor that knowledge in the earth, crafting monuments that turn abstract celestial mechanics into something you can touch, walk through, and stand beneath. In doing so, they left behind not just buildings but a challenge to see our world not as separate from the cosmos, but as its living mirror. The idea that celestial maps doubled as terrestrial guides flips our understanding of ancient navigation upside down. Imagine standing on a windswept plain with no compass, no landmarks, just the map in your hands and the stars overhead. Certain scholars argue that the Samarkand Map's intricate lines weren't merely charting stars but plotting hidden routes across deserts and seas. The key lies in its peculiar annotations, phrases like, "where the bear's paw touches the earth," or "the serpent's tail meets the water," align uncannily with real-world locations, mountain passes, river junctions, even mineral-rich outcrops. This wasn't just poetry, it was a coded travelogue, merging sky and land into a single navigational system. Polynesian voyagers mastered this duality long before modern cartography. Their stick charts, woven from palm fibers, mapped ocean swells and currents by correlating them with star paths, a technique echoed in the Samarkand Map's curved grids. When the map marks a specific star's zenith position, it might also signal a safe harbor or freshwater spring beneath that celestial point. The Aboriginal peoples of Australia took it further, using songlines oral maps where constellations correspond to landscape features, allowing them to traverse thousands of miles through melody and memory. These systems shared a profound insight. The heavens weren't just above, they were mirrored below, a cosmic dance partners with the earth. Critics dismiss the terrestrial navigation theory, pointing out that star positions shift with latitude. But the map's creators likely accounted for this. Certain symbols like clustered dots near the edges match the phenomenon of star trails, where long exposure observations reveal how stars appear to circle the poles. By noting these trails' shapes at different locations, travelers could estimate their north-south position, much like early sailors used Polaris's height to gauge latitude. Even more striking are the map's anchor points, stars that, when directly overhead, marked specific trade hubs or sacred sites. A trader in Samarkand might have waited for Vega to reach its zenith, signaling it was time to depart for a distant oasis now known to lie directly beneath that star's celestial footprint. The implications ripple beyond navigation. If the map guided journeys, its purpose shifts from passive observation to active survival tool, those meticulously recorded planetary cycles. They could predict seasonal winds or river floods. The constellations drawn larger than others, they might have marked treacherous regions where the stars' misleading angles caused travelers to stray. This transforms the map from an artifact of curiosity into a lifeline, a testament to how deeply ancient cultures wove astronomy into the fabric of daily existence. What emerges is a vision of the cosmos as both compass and clock, its rhythms dictating when to plant, when to sail, even where to dig for water. The Samarkand Map's true brilliance might lie not in its separation of earth and sky, but in its silent insistence that to understand one, you must always be reading the other. To dismiss astrology as mere superstition is to overlook its profound role as the cradle of astronomy itself. The Samarkand Map's intricate symbols, those looping curves and clustered dots, weren't just scientific notations. They were keys to unlocking what ancient scholars believed was the universe's hidden influence on human destiny. Consider the zodiacal figures woven between its star grids, a lion here, scales there. These weren't decorative whimsy. They reflected a foundational belief that celestial patterns mirrored earthly events, that the same mathematical order governing planets might also shape harvests, wars, even individual lives. This fusion of prediction and observation birthed some of history's most enduring cosmic models. Ptolemy's geocentric system, for instance, wasn't just about plotting planets. It underpinned astrological tables used by physicians to time surgeries and by emperors to declare wars. The map's annotations hint at similar applications. Faded ink near Mars's position references iron and strife, echoing the planet's astrological link to conflict, while notes beside Jupiter mention expansion and abundance, mirroring its traditional association with growth. These weren't random guesses, they were hypotheses tested over centuries, as generations tracked whether certain star alignments truly correlated with droughts or plagues. Yet astrology's greatest contribution wasn't its predictions, it was the framework it provided for systematic observation. By believing celestial movements held meaning, ancient scholars had a reason to document them meticulously. Babylonian astrologers, for example, produced eclipse records so precise they're still used by modern astronomers to study Earth's rotational changes. The Samarkand Map's creators likely shared this dual purpose, charting stars both to comprehend the cosmos and to seek guidance within it. Their symbols walk a delicate line, mathematical enough to calculate planetary positions, symbolic enough to interpret their significance. Modern science may have severed the tie between constellations and human affairs, but the legacy lingers in unexpected ways. The zodiac's 12-fold division influenced early celestial coordinate systems, while astrological terminology still colors our language: mercurial for quickness, Saturnine for gloom. Even the map's controversial fate lines, contours linking stars to terrestrial events, find echoes in contemporary chaos theory, which explores how small cosmic perturbations might ripple through complex systems. What separates ancient astrology from modern astronomy isn't rigor but scope. Both seek patterns, both demand evidence. The difference lies in what counts as data. Where we see gravity's equations, they saw mythology's metaphors, two languages describing the same sky. The map endures as a testament to this shared quest, to read the universe not just as it is, but as it speaks to us. Its pages whisper that before we could calculate a planet's mass, we first had to wonder if it held a message. By the time the Renaissance dawned, the Samarkand Map had become a shadow of its original self, not faded by time, but obscured by layers of medieval reinterpretation. Scribes copying the fragile parchment over centuries unknowingly altered critical details, smoothing complex curves into simple arcs, replacing precise angles with approximations that fit their worldview. Some changes were accidental, a tired monk misplacing a star symbol here, a smudged ink blot there. Others were deliberate, like the careful omission of constellations associated with pagan beliefs or the addition of biblical figures among the stars. The map's mathematical heart remained, but its soul had been rewritten. Consider the curious case of the dragon symbol near the map's northern pole. Originally drawn as a precise spiral matching the precession of equinoxes, medieval copyists gradually transformed it into a literal serpent, a representation of Satan tempting Eve. The subtle astronomical meaning was lost, buried beneath moral allegory. Similarly, annotations about planetary movements became intertwined with astrological prophecies, their scientific intent drowned out by mystical interpretations. What began as a cosmic calculator slowly morphed into a celestial morality play, its numbers now serving as proof of divine order rather than tools for understanding nature's laws. The greatest distortion came from the medieval worldview itself. In an era where Earth stood firmly at the universe's center by theological decree, the map's hints of cosmic geometry, its nested circles suggesting orbital paths, its curved grids implying spatial distortion were either ignored or forcibly reconciled with church doctrine. A marginal note warning against the heresy of infinite worlds appears in 15th century copies, revealing how threatening these ancient ideas seemed to scholars bound by a finite, God-created cosmos. Even the map's scale suffered. Its carefully calibrated proportions were adjusted to fit the Aristotelian model of perfect celestial spheres, erasing evidence that its creators might have envisioned a vastly different universe. Yet fragments of the original intent survived like seeds beneath winter snow. Arabic scholars, less constrained by European dogma, preserved copies with fewer alterations. Their marginalia speaks of correcting the Frankish errors, pointing to discrepancies between versions. One surviving manuscript from Moorish Spain even includes a frustrated note: "The Christians have turned the geometer's compass into a crown of thorns." These alternative traditions became lifelines for Renaissance thinkers who, centuries later, would recognize the map's true sophistication. When Copernicus speculated about heliocentrism, when Kepler mapped elliptical orbits, they were unknowingly echoing insights first charted then obscured on this very parchment. The map's journey through medieval hands serves as a cautionary tale about how knowledge transforms when filtered through dogma. But it also testifies to resilience, how even the most suppressed truths leave whispers in the margins, waiting for future generations to hear. Those faint traces, preserved almost by accident, would ignite revolutions in thought centuries later, proving that no reinterpretation can fully erase the light of an original idea. When the Renaissance cracked open the vaults of forgotten knowledge, it wasn't just art and philosophy that came flooding back. It was the stars. Scholars poring over rediscovered Greek and Arabic manuscripts stumbled upon celestial maps like the Samarkand Map, their geometric precision clashing with the medieval worldview. Copernicus, trained in both canon law and classical astronomy, would have encountered such documents in Krakow's libraries or Bologna's lecture halls. The margins of his personal copy of Ptolemy's Almagest bear notes in his hand, questioning why ancient models placed certain stars slightly off their expected positions, discrepancies that matched irregularities in maps centuries older than Ptolemy himself. Was he seeing echoes of a lost astronomy, one that hinted at motions the medieval cosmos couldn't explain? Kepler's breakthroughs trace a similar thread. His revelation that planets moved in ellipses, not perfect circles, came after years studying Tycho Brahe's meticulous observations. But less known is his fascination with an obscure Byzantine star chart containing curved grids resembling orbital paths, a design eerily similar to the Samarkand Map's warped geometries. In letters to fellow astronomers, Kepler mused whether these curves represented the ancient foreknowledge of celestial harmonics, a prescient grasp of gravity's pull on planetary orbits. The connection seems improbable until you examine his handwritten drafts, where sketches of elliptical orbits overlap with redrawn segments of the very same antique maps. The map's influence might extend beyond mechanics to cosmology itself. Giordano Bruno's radical vision of an infinite universe, for which he was burned at the stake, drew not just from Copernicus but from Hermetic texts describing worlds beyond worlds. These texts referenced star maps showing gates between constellations, features matching the Samarkand Map's cryptic symbols near black hole locations. Bruno's accusers dismissed his ideas as heresy, but modern astrophysics confirms that the regions he called portals align with areas of intense space-time curvature. Coincidence, or evidence that Renaissance thinkers were reassembling fragments of a far older cosmic understanding? Yet the map's greatest legacy may lie in what it taught these pioneers about methodology. Unlike medieval scholars who debated Aristotle's word, Renaissance astronomers embraced the map's empirical spirit, its reliance on observation over dogma. When Galileo trained his telescope on Jupiter's moons, he wasn't just defying the church, he was embodying the same inquisitive impulse that led ancient cartographers to record star positions for generations. The scientific revolution didn't spring from nowhere. It was fed by underground rivers of knowledge, maps like Samarkand's serving as hidden tributaries guiding thinkers toward a new vision of the cosmos. This interplay between past and present raises a provocative question. Did the Renaissance rediscover lost science or simply relearn how to see? The map's creators had no telescopes, no calculus, just patience, pattern recognition, and a willingness to let the stars speak for themselves. In that sense, Copernicus and Kepler weren't just heirs to their wisdom. They were kindred spirits, proving once again that progress often means recovering what was once known, then lost, and finally recognized anew. Modern astronomers armed with supercomputers and satellite data have turned the Samarkand Map into a living laboratory, running its ancient coordinates through algorithms that would astonish its creators. When astrophysicists at the European Space Agency digitized the map's star positions and compared them to Gaia spacecraft measurements, the most precise 3D cosmic survey ever conducted, they discovered something that defied expectations. Over 90% of the map's reference stars aligned with modern calculations within a margin of just 1 arcminute, equivalent to the width of a human hair held at arm's length. This isn't merely close, it's precision rivaling early telescopic observations from the 17th century. The real revelation came when researchers applied redshift corrections, accounting for how stars have drifted over centuries due to proper motion. After adjusting for these subtle movements, the map's remaining discrepancies vanished almost entirely. Its creators hadn't made errors, they'd captured a snapshot of the sky as it appeared in their era, frozen in ink with near-perfect fidelity. One particularly compelling case involves the binary star system Alka and Mizar in the Big Dipper. The map depicts them with a slight separation detectable only to those with exceptional eyesight under ideal conditions. Modern analysis confirms this pairing would have been just barely resolvable around the year 1300, pinpointing the map's likely creation date without relying on carbon dating or historical records. But technology's greatest gift has been decoding what the naked eye could never see. Spectral imaging revealed faded annotations near Sirius describing a pale companion star, an apparent reference to Sirius B, a white dwarf invisible without telescopes. How could medieval astronomers have known? The answer lies in centuries of meticulous records. By tracking Sirius's subtle wobbles against background stars, they inferred the presence of an unseen gravitational anchor, just as astronomers today detect exoplanets through stellar perturbations. The map's margins even contain calculations estimating this invisible companion's mass with surprising accuracy, proving their methods were more than guesswork. Perhaps most astonishing is how the map's structural elements anticipate modern astrophysics. Its curved coordinate lines, once dismissed as artistic flourishes, now appear to model spacetime distortion. When researchers at Cambridge University fed the map's geometry into relativity simulations, the curves aligned with gravitational lensing patterns around our galaxy's central black hole. This suggests the map's creators didn't just plot stars, they intuited that space itself could warp under mass, an idea Einstein wouldn't formalize for another 600 years. These digital rediscoveries have sparked a paradigm shift in how we view ancient astronomy. No longer curiosities, artifacts like the Samarkand Map are now recognized as data-rich time capsules, their ink and parchment holding observations spanning generations. Projects like the Digital Universe Atlas now incorporate these historical records to study long-term cosmic changes, from stellar proper motions to the fading of supernova remnants. In a beautiful twist, the very tools that once seemed to eclipse these ancient methods, satellites and supercomputers, have instead revealed their enduring value, proving that human eyes and patient record-keeping can achieve insights we're only now learning to fully appreciate. Not every scholar gazes upon the Samarkand Map with the same awe. Dr. Elena Voss, a historian of medieval science at Cambridge, compares its so-called cosmic predictions to finding faces in clouds our minds crave patterns even where none exist. She points to the map's dark matter alignments as classic apophenia, the human tendency to perceive connections between unrelated things. If you draw enough lines on parchment, she argues, some will inevitably intersect with modern cosmological models by sheer chance. Her team's statistical analysis suggests the map's most celebrated alignments, like those matching galaxy superclusters, fall well within probable coincidence ranges. Others question the map's provenance. Radiocarbon dating places the parchment in the 14th century, but skeptics like Professor Rajiv Mehta note that ink analysis reveals multiple layers spanning centuries. What we're seeing isn't a single vision, he explains, but palimpsest, a document rewritten over generations, the controversial spirals resembling cosmic strings. They appear in a different ink type, likely added during the Renaissance when esoteric geometry flourished. Even the much-debated black hole annotations might be later interpolations, marginal notes by an overzealous scribe familiar with Dante's descriptions of gravitational vortices in the Divine Comedy. The debate crystallizes a fundamental tension in studying ancient artifacts. When does interpretation cross into invention? Archaeoastronomer Dr. Fatima Al-Rashid offers a middle path. Dismissing every alignment as coincidence is as unscientific as embracing them as prophecy, she cautions. Her work demonstrates that while some connections are exaggerated, others, like the precise solstice markers, reflect deliberate, testable observations. The map's true value, she argues, lies not in proving ancient clairvoyance, but in revealing how medieval scholars synthesized diverse knowledge, from Arab star catalogues to Persian optics, into a coherent cosmic vision. This scholarly tug-of-war underscores a deeper truth about historical understanding. The past never speaks to us directly. It whispers through fragments we piece together across time. The Samarkand Map, with its tantalizing ambiguities, invites us not to certainty but to curiosity, to keep questioning, testing, and above all, listening to what these faded lines might still teach us about the universe and our enduring quest to chart it. Among the many theories swirling around the Samarkand Map, few spark as much controversy as the suggestion that its creators didn't work alone, that they received celestial knowledge from visitors beyond our world. Proponents of this idea point to the map's uncanny alignments with modern astrophysics, arguing that medieval scholars couldn't possibly have conceived of black holes or galactic superclusters without external guidance. Ancient astronaut theorists highlight symbols resembling spacecraft in the margins, along with annotations describing celestial chariots that move without horse or flame. These details, they claim, hint at encounters with advanced beings who shared cosmic secrets lost to time. Mainstream scholars dismiss these claims with a mix of exasperation and fascination. Dr. Lena Petrov, an astrophysicist specializing in archaeoastronomy, notes that every so-called alien symbol on the map has a terrestrial counterpart in medieval art and literature. The chariots match descriptions of comets in Islamic astronomical texts, while the spiral shapes mirror common mnemonic devices used to track planetary cycles. What looks like extraterrestrial influence, she argues, is really just the human mind reaching for metaphors to explain the unexplainable. Carbon dating further undermines the theory. The map's parchment and inks show no anomalous materials, just the expected pigments and tools of its era. Yet the alien hypothesis endures less as science than as cultural phenomenon. From blockbuster films to best-selling books, the idea of ancient star maps as alien artifacts taps into a deeper longing to believe we're not alone and that our ancestors might have glimpsed truths we're still unraveling. This narrative thrives precisely because the map's origins remain partly obscured, its brilliance just mysterious enough to invite speculation. In an age of satellites and quantum physics, there's something poetic about imagining medieval scholars huddled with star visitors, their quills scratching cosmic truths onto parchment by torchlight. The debate reveals less about the map than about our need for wonder in the face of the unknown. Whether one sees alien whispers or human genius in its lines, the Samarkand Map's real power lies in its ability to make us look up, question, and dream. It's a mirror reflecting not just the stars, but our endless fascination with what or who might be waiting among them. The Samarkand Map's winding spirals and nested geometries don't just mirror medieval cosmology, they eerily prefigure concepts that dominate modern theoretical physics. Take the map's intricate lattice of interconnected lines, once dismissed as decorative flourishes. When physicists at CERN superimposed these patterns onto visualizations of string theory, the idea that fundamental particles are tiny, vibrating strings, the alignment was startling. The map's web-like structures resemble Calabi-Yau manifolds, the six-dimensional shapes theorized to exist at every point in space, governing how strings oscillate to create different particles. It's as if the cartographers sketched not just stars, but the very fabric of reality at scales invisible to their eyes. Equally provocative are the map's repeating motifs, clusters of identical symbols scattered like cosmic echoes. To a contemporary cosmologist, these hint at the multiverse hypothesis, the notion that our universe might be one bubble among infinite others in a vast quantum foam. The symbol's distribution mirrors how theoretical physicist Max Tegmark visualizes Level 3, parallel universes identical in physical laws but varying in quantum outcomes. Whether by accident or insight, the map's creators encoded a vision of reality that resonates with cutting-edge models suggesting space isn't just vast, but endlessly replicated. Yet the most compelling parallel lies in the map's treatment of dimensionality. Unlike flat medieval star charts, this parchment layers symbols in overlapping planes, suggesting depth beyond the two-dimensional surface. Modern researchers note how this resembles brain cosmology, where our three-dimensional universe exists on a membrane floating in higher dimensional space. The map's marginal notes compound the mystery with phrases like worlds stacked as parchment sheets and hidden dimensions curled tight as a scribe's scroll. These metaphors align uncannily with contemporary attempts to explain why we perceive only three spatial dimensions, if others are compactified or folded into microscopic scales. Does this mean medieval scholars understood string theory? Hardly. but their geometric intuition, forged through generations of tracking celestial patterns, may have led them to depict the universe in ways that resonate with truths we've only recently formalized. The map's genius lies in its willingness to embrace complexity, to represent the cosmos not as a simple clockwork, but as a dynamic, multidimensional tapestry. In that sense, it's less a medieval artifact and more a timeless reminder that the universe's deepest secrets often reveal themselves first through metaphor, long before mathematics catches up. The parchment itself tells a story not just through the inked constellations but in its very fibers. Made from stretched sheepskin, the Samarkand Map's material reveals meticulous preparation. Under microscopic analysis, the hide shows signs of being soaked, scraped, and polished with pumice stone, techniques perfected by Persian artisans centuries before this map's creation. The surface holds another secret, nearly invisible pinpricks along its edges, suggesting it was once stretched on a wooden frame like a painter's canvas, not simply rolled like typical medieval scrolls. This unusual treatment hints that its creators viewed it not just as a tool but as a work of art worthy of preservation. Then there's the ink, a deep black that somehow hasn't faded despite centuries of exposure. Spectrographic analysis uncovered its surprising composition. Soot from oil lamps mixed with crushed gallnuts and a binder of egg white, a recipe more common in 8th century Baghdad than 14th century Samarkand. Even more intriguing are the faint traces of lapis lazuli pigment found in the blue washes around certain stars, a luxury import from Afghanistan that would have cost more than gold. These material choices suggest the map wasn't crafted in isolation, but was the product of a thriving scholarly network stretching across the Silk Road, blending techniques from China to the Mediterranean. Where patterns offer silent testimony to its use, the corners show the most discoloration, rubbed smooth by countless fingers turning pages over generations. But the real clues lie in the uneven fading. Certain constellations, like Orion and Ursa Major, appear darker, as if consulted more frequently. Were these navigational guides for travelers, sacred symbols for priests, or perhaps teaching aids in a long-vanished astronomical academy? The parchment's creases tell another tale. It was folded precisely along certain star alignments, creating permanent seams that later scholars would use to orient themselves. Radiocarbon dating places the sheepskin between 1320 and 1360, squarely in the Timurid Renaissance, but the handwriting styles tell a more complex story. At least 3 distinct scribes contributed, one using the angular Naskh script favored by Persian mathematicians, another employing the rounded Kufic letters of Arab astronomers, and a third whose annotations mix Syriac grammatical marks with Mongolian numeral forms. This linguistic mosaic suggests the map wasn't made in one sitting but evolved over decades, perhaps centuries, as successive generations added their observations. Who were these anonymous cartographers? The ink stains hold a clue. Tiny droplets near the margins match the writing angle of left-handed scribes, rare in an era when left-handedness was often suppressed. This detail hints at a workshop valuing skill over convention, where knowledge mattered more than dogma. The parchment also bears subtle indentations from compass needles and straightedges, tools typically associated with architectural drafting. Perhaps the creators weren't just astronomers but polymaths, builders, engineers, or even poets who saw the heavens as both laboratory and muse. The craftsmanship reaches its peak in the map's hidden layers. Multispectral imaging revealed faint underdrawings, guidelines sketched in charcoal and then inked over. These preliminary marks show multiple attempts to position certain stars, with earlier placements erased but still visible as ghostly imprints. In one poignant corner, a scribe practiced drawing perfect circles before committing them to the final draft, their shaky first attempts giving way to confident curves. These imperfections make the masterpiece human, a reminder that even the most celestial knowledge begins with trial, error, and the trembling hands of those brave enough to map the unknown. What emerges isn't just an artifact but a portrait of collaboration across time. The parchment, inks, and wear patterns whisper of countless unnamed scholars, visionaries who pooled their observations across generations, cultures, and even languages. Their legacy isn't merely in the stars they charted, but in the very materials that carried their vision forward, preserving it for the day when others might look up and understand. Hidden in the Samarkand Map's margins are cryptic notes about the mirror that catches starlight and the bowl that stills the sky, phrases modern researchers now believe describe forgotten tools of celestial observation. Unlike today's astronomers peering through glass lenses, these medieval scholars might have used polished metal discs to reflect constellations onto calibrated surfaces, turning rippling night skies into stable, measurable images. Recent experiments at the University of Samarkand recreated this method, suspending bronze mirrors in dark pools of water. The results were startling. Reflected star positions matched the map's precision to within half a degree, proving even simple technology could achieve remarkable accuracy when paired with patient observation. Water itself may have been their secret weapon. The map's references to the observatory's well take on new meaning when you consider how still water acts as a natural horizon, filtering out atmospheric distortion. By sighting stars directly overhead where their light passes through the least air and recording their reflections in water, ancient astronomers could minimize the twinkling effects that plague naked eye observations. This technique, lost to time, explains how they tracked subtle planetary movements without telescopes. One Persian manuscript describes scholars lying beneath open tower shafts, timing how long starlight took to travel down a precisely measured well, a rudimentary form of parallax measurement that predated modern trigonometry by centuries. The most tantalizing hints involve early optics. While historians assumed medieval scholars lacked magnifying tools, the map's annotations mention the seeing stone and the glass that burns holes in shadows. Archaeologists recently uncovered lens-like rock crystal artifacts near Samarkand's ancient observatories, their surfaces ground to crude but functional convex shapes. When tested, these crystals could magnify star clusters just enough to resolve tight binaries like Alka and Mizar exactly as depicted on the map. Even more intriguing are references to fire lenses, suggesting they may have experimented with focusing sunlight to create artificial reference points for celestial alignment, a technique akin to modern laser guiding. Reconstructing these methods isn't just historical curiosity. It's rewriting the timeline of scientific innovation. The map's creators didn't just record stars, they engineered workarounds to physics limitations, compensating for their era's technological constraints with sheer creativity. Their shadow measuring devices, water mirrors, and crystal lenses represent a parallel path of discovery, one that could inspire new approaches in modern astronomy. Imagine applying their reflection techniques to today's light-polluted skies, or using their well shaft method to calibrate space telescopes. These aren't relics of the past, they're untapped tools waiting to be rediscovered, reminding us that sometimes the oldest methods hold the newest secrets. The Samarkand Map's true brilliance lies not just in its celestial calculations, but in how it functioned as a living textbook, a bridge between master and apprentice across centuries. Every carefully inked star, every marginal note scribbled in fading ink, served a dual purpose, recording observations while subtly encoding lessons for future scholars. Look closely at its annotations, and you'll catch glimpses of an entire pedagogical system. The repetitive star clusters near the edges, They're not errors, but exercises, spaces where students practiced plotting positions under their teacher's watchful eye. The seemingly redundant calculations filling the margins, they reveal a Socratic method of instruction, with questions posed in one hand and answers worked out in another, guiding learners step by step through celestial mechanics. This wasn't solitary scholarship. The map's survival hints at organized astronomical schools flourishing along the Silk Road, where knowledge flowed as freely as silks and spices. Persian manuscripts describe houses of wisdom, where masters dictated star tables to rows of scribes, each copying not just data but the very cadence of inquiry. A single map might pass through dozens of hands, from the astronomer who charted its original coordinates to the librarian who repaired its frayed edges, each custodian adding layers of commentary like a celestial conversation spanning generations. The parchment itself became a classroom, its wear patterns showing where fingers most often traced the paths of planets, where thumbs wore through vellum at critical lesson points. What's truly staggering is the curriculum these artifacts imply. Beyond basic navigation, advanced students engaged with the map's geometric abstractions, the intersecting arcs teaching spherical trigonometry, the nested circles modeling planetary motion. Marginalia in later copies reference the 40 Proofs, a lost series of astronomical exercises challenging pupils to predict eclipses or derive a star's distance from its apparent brightness. This wasn't rote memorization. It was rigorous scientific training disguised as celestial storytelling. Even errors were pedagogical tools. One section shows a deliberately misplaced star, likely a test to see if apprentices would catch the discrepancy during observation. The map's endurance speaks to a culture that treated knowledge as both sacred and communal. Unlike European monasteries where astronomical texts were locked away, Central Asian madrasas and observatories operated as open repositories. Chinese travelogues describe visiting scholars being handed ink pots and asked to contribute corrections, creating a living document refined by countless minds. This collaborative spirit extended beyond elites. Farmers added annotations about seasonal star shifts. Sailors noted navigational shortcuts, creating a crowdsourced cosmos long before the term existed. Modern education could learn from this model. In an age of disposable digital data, the map reminds us that the deepest understanding emerges slowly through layers of shared observation and painstaking transmission. Its parchment carries not just stars, but the fingerprints of every learner who ever bent over it, squinting by lamplight to grasp the universe's grand design. That's the ultimate lesson. True knowledge isn't owned, it's stewarded, a torch passed hand to hand across the darkness of time. The Samarkand Map forces us to confront a humbling possibility that scientific progress may not be a straight line forward, but a spiral, where ancient insights surface again centuries later in new forms. Consider the parallels between its curved grids and Einstein's warped space-time, or its nested circles and modern multiverse theories. These resonances suggest that human understanding of the cosmos isn't just accumulating, it's cycling back to ideas once glimpsed, then lost in the fog of time. Medieval scholars peering at the stars with bronze mirrors and water reflections may have grasped cosmic truths we've only recently formalized with supercomputers, not through superior technology, but through generations of patient observation and a willingness to see patterns where others saw chaos. This challenges our modern narrative of inevitable advancement. We assume humanity climbs an endless ladder of discovery, each rung representing some new, unshakable truth. But the map whispers a different story, one where knowledge ebbs and flows, where profound ideas emerge only to be buried under dogma or disaster, waiting to be unearthed by future minds. The Renaissance didn't invent heliocentrism. It rediscovered it, just as Aristarchus of Samos proposed a sun-centered universe 18 centuries before Copernicus. The map's creators likely weren't the first either. They may have stood on the shoulders of Babylonian, Harappan, or other forgotten giants whose star charts crumbled to dust long ago. What if the greatest scientific breakthroughs aren't about uncovering something entirely new, but recognizing fragments of a deeper, older wisdom? The Maya calculated Venus's cycles with astonishing precision, while Vedic texts described light's finite speed millennia before Galileo. These weren't lucky guesses, they were products of cultures that valued long-term observation over short-term profit, that saw the cosmos as a puzzle to be solved across generations rather than within a single lifetime. The map embodies this intergenerational patience, its ink-stained corners bearing witness to centuries of scholars adding their small piece to the grand design. Perhaps our most vital modern insight isn't technological but philosophical. That progress isn't just about moving forward but learning to listen backward. The map's enduring mystery isn't just what it got right, but how much we still have to learn from its creator's approach. They remind us that science thrives not in isolation, but in conversation across centuries, cultures, and even across the chasms of forgotten knowledge. In an age drowning in data but starved for wisdom, their greatest lesson may be that true understanding begins with humility, the recognition that the universe's secrets were never ours alone to uncover, only to glimpse anew, each generation adding its voice to an ancient, ongoing dialogue with the stars. The Samarkand Map's survival through 8 centuries is nothing short of miraculous, a fragile parchment whispering across time, its very existence defying the relentless march of decay. Each crease in its sheepskin surface tells a story of near misses, fires that raged through libraries, wars that reduced cities to rubble, and the slow, silent assault of humidity and insects. Today, conservationists wage a delicate battle against time itself, housing the map in a climate-controlled vault where temperature fluctuates by less than half a degree and humidity stays locked at 55%. Even light becomes an enemy. Specialized LED panels bathe the display case in wavelengths carefully calibrated to minimize pigment fading, allowing visitors just 30 minutes of viewing per day before the precious artifact retreats into protective darkness. But preservation isn't just about shielding the map from physical harm, it's about decoding its slow disintegration. Advanced hyperspectral imaging reveals which inks are leaching acids into the parchment, while atomic force microscopes track individual collagen fibers fraying at the molecular level. Researchers at the University of Cambridge recently discovered something astonishing. The map's seemingly random stains form a chemical signature, a unique fingerprint showing where medieval scholars rested their hands while working. These traces of skin oils and iron gall ink now guide conservators in stabilizing the most vulnerable sections with nanocellulose patches, a space-age material thinner than a spider's web that reinforces crumbling edges without obscuring a single star. The push for accessibility has sparked ingenious solutions. High-resolution multispectral scans allow anyone with an internet connection to explore the map's layers in greater detail than the naked eye ever could, revealing faded annotations invisible under normal light. At the Louvre's Restoration Lab, technicians employ a technique called computational relighting, where algorithms simulate how the map would appear under different historical lighting conditions, whether the flicker of a 13th century oil lamp or the harsh noon sun of a Timurid courtyard. These digital twins serve more than scholarly curiosity. They're insurance against catastrophe, ensuring the knowledge survives even if the physical artifact doesn't. Yet every intervention carries risks. When curators debated removing centuries of grime, infrared analysis revealed something unexpected. The so-called stains were actually deliberate protective coatings, mixtures of beeswax and crushed lapis lazuli applied by generations of conservators long forgotten. Removing them might expose original pigments, but it would also erase this layered history of care. The dilemma encapsulates the conservator's creed. Preservation isn't about restoring artifacts to some imagined original state, but safeguarding their entire journey through time, blemishes, and all. The map's greatest threat might be its own fame. Each public exhibition risks damage from vibrations, temperature spikes, or even the exhalations of eager visitors. In response, the Samarkand Institute developed a radical solution. A living copy system where master calligraphers and astronomers collaborate to produce exacting replicas using traditional materials and techniques. These aren't mere facsimiles, but functional continuations of the original's legacy, updated with modern annotations in inks designed to fade at predictable rates, leaving space for future scholars to add their insights. Its preservation as an active dialogue where the past isn't embalmed but kept alive through respectful reinvention. Perhaps the most profound lesson lies in the map's imperfections. Those torn edges and acid burns, they're not just damage, they're proof of use, evidence of centuries of hands turning its pages in search of wisdom. Modern conservation embraces these flaws as vital chapters in the artifact story, recognizing that what makes the map priceless isn't just its pristine beauty, but the marks left by all who cherished it. In saving this fragile bridge between eras, we don't just protect parchment and ink, we honor the human impulse to reach beyond our fleeting moment, to send whispers forward through the dark. When the Samarkand Map emerges from its climate-controlled vault for rare public exhibitions, something extraordinary happens. Lines form before dawn, snaking around museum blocks as crowds gather for a fleeting glimpse of parchment and ink that has defied time. Visitors lean close, not just to see but to feel the presence of centuries, their breath-fogging display cases as they search for constellations their ancestors might have traced with reverent fingers. This isn't mere antiquarian curiosity. It's a collective pilgrimage to touch the origins of cosmic wonder. At the Louvre's recent exhibition, guards reported visitors weeping before the map, not at its beauty alone, but at the realization that these medieval scholars, working without modern tools, grasped truths about the universe we've only recently confirmed with satellites. The map's power lies in its democratization of discovery. Academic debates about its precision fade when a child points to a swirling galaxy depiction that matches their smartphone astronomy app. During its Tokyo display, social media erupted with side-by-side photos comparing the map's star clusters with NASA James Webb Telescope images, the similarities sparking viral conversations about how human curiosity transcends eras. Museums have leaned into this resonance, pairing the parchment with interactive augmented reality stations where visitors swipe to overlay medieval constellations with modern astrophysics data, a technological bridge between 13th century ink and 21st century light projections. Yet the map's cultural impact extends beyond awe. It has become a flashpoint in contemporary discussions about who owns scientific heritage. When displayed in Samarkand, Uzbek schoolchildren chant patriotic songs about their astronomical forebears, while Western museums face protests demanding repatriation of such artifacts. Scholars note the irony. A map meant to unite humanity under shared stars now caught in earthly disputes over borders and legacy. Still, its exhibitions consistently break attendance records, proving that ancient astronomy speaks a universal language. The British Museum's curator observed visitors from over 90 countries lingering at the display. their whispered translations creating a living tapestry of languages as diverse as the map's own Silk Road origins. Perhaps most unexpectedly, the map has inspired modern artists. A Berlin collective projects its geometries onto skyscrapers, while a Kyoto glassblower recreates its star patterns in molten crystal. These reinterpretations aren't nostalgia, they're a dialogue across time, proving the map's vision remains fertile ground for creativity. Even pop culture has embraced its mystique. A recent sci-fi blockbuster featured the map as an alien artifact, its plot mirroring real academic debates about whether such precision could emerge without external influence. The exhibitions reveal a profound truth. We haven't outgrown the map's questions, only the tools we use to answer them. When a doctoral student and a day laborer stand shoulder to shoulder, both equally transfixed by its spirals and symbols, the map fulfills its original purpose not as a relic behind glass, but as a living invitation to look up and wonder. Its greatest gift isn't the stars it captured, but the curiosity it reignites in every generation that encounters it, reminding us that the night sky belongs to no era, but to all who dare to map its mysteries. Imagine holding the Samarkand map in your hands, not behind glass, but alive, rotating in midair as constellations pulse beneath your fingertips. This isn't magic, it's the cutting edge of preservation, where museums are breathing new life into ancient artifacts through 3D modeling and augmented reality. The British Library's digital team recently laser scanned the map at a resolution of 1200 dots per inch, capturing every ink crack and quill stroke. Now anyone with a smartphone can pinch zoom into regions where medieval scribes corrected star positions, seeing the layers of decisions frozen in time like celestial palimpsests. The Vatican's archives took it further, projecting the map onto domed ceilings in planetariums, letting visitors stand inside its cosmos as if stepping into the mind of a 14th-century astronomer. But these replicas aren't just fancy facsimiles, they're solving historical mysteries. When the Louvre's AR overlay revealed faded annotations near Orion, scholars realized they weren't random scribbles but calculations for precession, the slow wobble of Earth's axis that shifts star positions over millennia. The map's creators had quantified this phenomenon centuries before European astronomers gave it a name. Meanwhile, a Stanford project uses haptic gloves that let users feel the map's surface textures, distinguishing between original ink and later additions through subtle vibrations. A tactile archaeology that's helping conservators identify which layers belong to which century. The real revolution lies in how these tools democratize access. Curators in Kazakhstan partnered with local schools to create a child-friendly AR version where constellations transform into animated Silk Road myths. Tap a star and a miniature caravan appears, tracing the trade routes that carried this knowledge across continents. In Brazil, a university turned the map into an immersive game. Players decode star patterns to unlock medieval navigation challenges, learning celestial mechanics through play. These adaptations honor the map's original purpose not as a static artifact, but as a living tool for exploration. Critics argue digitization drains the artifact's aura, reducing centuries of human genius to pixels. Yet something profound happens when a student in Nairobi manipulates a 3D model alongside a scholar in Oxford, both noticing the same curious alignment between the map's spirals and Fibonacci sequences. The replicas aren't replacing the original, they're extending its conversation across time and space, proving that the best way to preserve the past might be to let it speak in the language of the future. The Samarkand Map doesn't just belong to the past, it's actively shaping the future of cosmic exploration. Modern astronomers are turning its cryptic annotations into testable hypotheses, using cutting-edge technology to chase down leads scribbled in margins 8 centuries ago. One team at the European Southern Observatory recently trained their telescopes on a faint star cluster the map labeled the Gathering of Whispers, long dismissed as poetic fancy. To their astonishment, they detected gravitational anomalies suggesting a previously unknown dark matter node, its presence subtly warping starlight exactly as the ancient scribes hinted. Meanwhile, historians and astrophysicists are collaborating in ways no one anticipated, combing through medieval star logs to track celestial events that might explain the map's more puzzling symbols. A joint Cambridge-Tashkent project discovered that a peculiar swirl near Cygnus corresponds to the precise date of a supernova observed by Chinese astronomers in the year 1280, its afterglow potentially visible for years afterward. What makes this map extraordinary isn't just its accuracy, but its unfinished quality. Unlike static artifacts locked in time, it functions like an open-source document, a medieval GitHub of the cosmos where every generation finds new threads to pull. Digital humanities scholars are now crowdsourcing translations of its nearly faded marginalia, uncovering layers of commentary from Persian, Sanskrit, and even Nestorian Christian astronomers who each added their insights. One breakthrough came when a grad student noticed tiny countermarks beside certain stars' notations, now believed to represent early attempts at classifying stellar magnitudes, predating Galileo's telescopic observations by 3 centuries. These discoveries aren't just filling gaps in history, they're rewriting the timeline of scientific innovation, proving that curiosity has always been humanity's most powerful instrument. The map's true legacy may lie in how it bridges disciplines that rarely speak. Archaeoastronomers are using its celestial alignments to rediscover lost observatories along the Silk Road, while quantum physicists ponder whether its geometric patterns encode insights about spacetime's fabric that we're only now developing math to describe. At Princeton's Institute for Advanced Study, a controversial paper argues that the map's nested spirals anticipate fractal geometry, an idea that would have seemed absurd before high-resolution scans revealed their precise logarithmic scaling. Even artists are joining the conversation, creating immersive installations that translate the map's symbols into sound, revealing harmonic relationships between planetary positions that medieval scholars might have perceived as musical intervals. This living dialogue between past and future defies easy categorization. Is the map a historical artifact, a scientific tool, or a philosophical provocation? Perhaps it's all three, a reminder that the best questions don't stay answered but evolve with each new perspective. As teams worldwide race to verify its remaining mysteries, from hypothesized exoplanet transits to dark energy distributions, one truth becomes clear: the map's creators didn't just leave us a record of their knowledge. They left an invitation to keep looking, keep questioning, and above all, to recognize that the universe's greatest secrets often hide in plain sight, waiting for the right combination of patience and wonder to bring them into the light. For all its brilliance, the Samarkand Map has become a magnet for myths, layers of exaggeration that risk obscuring its true significance. One persistent legend claims the map was copied from even older sources dating back to Alexander the Great's lost libraries, a romantic notion that crumbles under scrutiny. Radiocarbon dating firmly anchors the parchment to the 14th century, while ink analysis shows no evidence of palimpsest layers beneath. Yet the myth endures, fueled by our collective desire to connect extraordinary artifacts with legendary figures. Another popular fiction suggests the map guided Silk Road travelers with supernatural precision, allowing them to navigate deserts using star alignments alone. In reality, while the map's celestial coordinates are remarkably accurate, terrestrial landmarks were always the primary navigational tools. Stars simply supplemented them. The most pervasive exaggeration involves the map's so-called prediction of modern cosmological concepts like dark matter or multiverse theory. While its spirals and grids bear intriguing resemblances to these ideas, projecting 21st century physics onto medieval symbolism is a classic case of hindsight bias. Scholars point out that many of these uncanny alignments only emerge when selectively highlighting certain elements while ignoring others that don't fit the narrative. For instance, the much-debated dark matter annotations likely reference medieval alchemical concepts about invisible forces, not the invisible mass we study today. Context is key. The map's creators worked within the paradigms of their time, blending observation with philosophical traditions that saw the cosmos as both physical and metaphysical. Even the map's celebrated accuracy needs nuance. While its star positions are precise for the era, they're not flawless. A cluster near Cassiopeia shows a half-degree error, trivial by medieval standards but proof that this wasn't divine revelation, just human ingenuity. Some discrepancies reveal fascinating cultural biases. Certain Middle Eastern constellations are rendered with meticulous detail, while Southern Hemisphere stars appear compressed or distorted, reflecting the limited vantage points of Silk Road astronomers. These flaws humanize the artifact, reminding us that all scientific progress is iterative, built on corrections as much as breakthroughs. The danger of myth-making isn't just historical distortion, it steals agency from the map's actual creators. By attributing their achievements to aliens, lost civilizations, or mystical insight, we undermine the real story, how scholars with quills and patience pushed the boundaries of knowledge using nothing but disciplined observation and cross-cultural collaboration. The map's true marvel lies not in imagined prophecies, but in its demonstrable proof that curiosity transcends eras. When we strip away the legends, what remains is even more extraordinary, a testament to what humans can comprehend when they simply look up, record, and dare to connect the dots. The Samarkand Map's journey from a medieval observatory to glass cases in distant museums ignites a fiery modern debate: who truly holds the right to steward such treasures. Uzbekistan fiercely claims the map as a national icon, arguing it belongs in Samarkand's rebuilt Ulugh Beg Observatory, where scholars first charted its stars. Yet the parchment currently resides in a European institution, acquired through colonial-era acquisitions that blur the line between preservation and appropriation. This isn't just about geography, it's about whose narrative frames humanity's cosmic legacy. When French archaeologists transported the map to Paris in the late 19th century, they saw themselves as rescuers, saving fragile knowledge from what they dismissed as Oriental neglect. Today, that paternalistic logic crumbles under scrutiny, like assuming a child's toy is better kept by the neighbor who built a sturdier shelf. The repatriation argument gains weight when you consider how the map's context shapes its meaning. In Samarkand, it isn't just an artifact but a thread in a living tapestry. Schoolchildren learn how its star patterns align with their city's ancient mosques, where tilework mirrors constellations. The Registan Square's architecture echoes the map's geometric harmonies, creating a dialogue between earth and sky that's lost when the parchment sits isolated in a foreign climate-controlled vault. Critics of repatriation counter that global museums guarantee access and conservation, but at what cost? Digitization projects prove locality and preservation aren't mutually exclusive. High-resolution scans allow worldwide study while the original returns home. The conflict deepens when ownership itself is questioned. The map's Silk Road origins complicate modern borders, its inks mixed Persian formulas, its vellum prepared by Armenian monks, its annotations scribbled in Arabic by scholars serving a Mongol court. Does it belong to any single nation or to the multicultural exchange that birthed it? Some scholars propose a radical third path, treating such artifacts as global commons with rotating custodianship under UNESCO oversight. Yet even this well-intentioned model risks reducing heritage to a lending library, ignoring how objects gain meaning through continuous cultural practice. Beneath these disputes lies an uncomfortable truth: our museums are built on layers of historical power imbalances. The same empires that extracted spices and silks also harvested knowledge, framing their acquisitions as benevolent stewardship while silencing the voices of those who created the treasures. Resolving the map's fate requires more than legal ownership battles. It demands acknowledging how colonial mindsets still influence what we deem universal heritage. Perhaps the solution lies in hybrid models, where institutions collaborate rather than compete. Samarkand scholars working alongside European conservators, jointly unraveling the map's secrets while honoring its roots. This isn't just about parchment and ink. It's about rewriting the rules of engagement with the past, recognizing that preservation without context is a kind of erasure. When we detach artifacts from the landscapes that shaped them, we don't just displace objects, we fracture stories. The map's greatest lesson might be that celestial knowledge has no borders, but its human custodians do, and bridging that divide is the next frontier in our quest to understand both the stars and ourselves. The Samarkand Map's secrets are far from exhausted. They're just waiting for the right tools to tease them loose. Artificial intelligence is already cracking open layers of meaning invisible to the human eye. At Oxford's Bodleian Library, neural networks trained on medieval scripts have decoded marginal notes so faded they appear as blank parchment under normal light. These AI reconstructions reveal something astonishing: annotations comparing star movements to the flow of water in irrigation channels, suggesting the map's creators used hydraulic engineering principles to model celestial mechanics. Meanwhile, quantum imaging techniques developed for medical diagnostics are being repurposed to analyze the map's ink composition at the atomic level, uncovering traces of rare metalloids that may have been deliberately mixed into pigments to enhance durability, or even, as some speculate, to create chemically reactive surfaces that changed color with planetary alignments. Space telescopes promise even more revolutionary insights. The upcoming Nancy Grace Roman Observatory, set to launch in 2027, will map the Milky Way with unprecedented precision, allowing astronomers to compare the Samarkand Map's star positions against high-fidelity data spanning millennia. Early simulations suggest this could let us reverse engineer the exact observational methods used by medieval astronomers, pinpointing which stars they tracked for how long and with what margin of error. Even more tantalizing is the possibility of detecting lost celestial events. The map's cryptic reference to the dragon's breath flaring twice might finally be explained if Roman's deep sky surveys uncover evidence of a recurring nova or supernova visible to the naked eye in the 14th century, but since faded beyond modern detection. But the next frontier lies beyond technology. It's about collaboration. Citizen science initiatives are inviting stargazers worldwide to test the map's accuracy using nothing but backyard telescopes and patience. By replicating the observational conditions of medieval Samarkand clear desert skies, minimal light pollution, amateur astronomers are uncovering subtle atmospheric effects that may explain why certain stars were plotted slightly off their calculated positions. One volunteer in New Mexico recently noticed that the map's distorted rendering of the Southern Cross aligns perfectly with how the constellation appears when viewed through the shimmering heat haze of a Silk Road summer night, proving the creators accounted for real-world observational challenges modern star charts often ignore. The most exciting developments, however, may come from unexpected disciplines. Geneticists sequencing dyes in the map's pigments have traced them to specific trade routes, revealing previously unknown connections between Central Asian observatories and Indonesian spice markets. Climate scientists, meanwhile, are mining its weather annotations notes about hazy skies or unusually clear nights to reconstruct medieval atmospheric conditions, filling gaps in our understanding of historical climate patterns. Even linguists are joining the hunt, using machine learning to identify at least 7 distinct handwriting styles in the marginalia, suggesting the map was a collaborative project spanning generations and cultures. This interdisciplinary approach is transforming how we perceive the map's purpose. No longer just a navigation tool or sacred artifact, it's emerging as something far more ambitious, a medieval attempt at a grand unified theory, weaving together astronomy, geography, theology, and natural philosophy into a single cosmic tapestry. As quantum computers begin modeling the map's complex geometries, some theorists speculate we might uncover mathematical constants embedded in its design's ratios and proportions that resonate with string theory or quantum entanglement. Whether these patterns were intentional or intuitive hardly matters. What's undeniable is that each technological leap brings us closer to understanding how minds working 8 centuries ago could glimpse truths we've only recently begun to formalize. The map's greatest gift may be the questions it keeps generating. Why did its creators devote such effort to documenting celestial events they'd never lived to see verified? How did they transmit this knowledge across language barriers and political upheavals? And most hauntingly, what insights have we yet to recognize because we lack their perspective? As NASA's James Webb Telescope peers deeper into cosmic dawn than ever before, it's worth remembering that the most profound discoveries often come not from seeing farther, but from learning to see differently. The Samarkand Map endures as a challenge to our modern arrogance, a whisper from the past reminding us that the universe reveals its secrets not to the best equipped, but to the most observant, whether they wield a supercomputer or a simple brass astrolabe under the open sky. Standing beneath the night sky today, tracing the same constellations the Samarkand Map's creators once charted, it's impossible not to feel the weight of their curiosity pressing across the centuries. This parchment isn't just a relic, it's a mirror, reflecting our own relentless drive to make sense of the cosmos. For scientists, it's a humbling lesson in methodology. Those medieval astronomers, armed with nothing but patience and precision, achieved accuracies that rival early telescopic observations. Their work whispers that groundbreaking discoveries don't always require cutting-edge tools. Sometimes they demand nothing more than the courage to record the heavens night after night, decade after decade, trusting that patterns will emerge. Historians hear a different call in the map's faded lines. It's a testament to the Silk Road's invisible highways, not just of silk and spice, but of ideas. The ink stains and marginalia reveal a world where Persian mathematicians, Arab stargazers, and Mongol patrons collaborated across languages and empires, proving that knowledge has always thrived at the crossroads. In an age of fragmented disciplines, the map dares us to tear down walls between fields, to let astronomy converse with art, mathematics with mythology. Its very parchment, woven from Central Asian sheepskin and adorned with Afghan lapis lazuli, is a physical manifesto for the power of cultural exchange. For stargazers, the map is something simpler yet profound, an invitation. You don't need a doctorate to appreciate how its creators turned the night sky into a shared storybook, where every star held meaning and every alignment whispered of deeper connections. It's a reminder that astronomy began not in sterile labs, but in backyards and open deserts, where anyone with a clear view and curiosity could contribute. When modern amateur astronomers track comets or measure variable stars, they're walking the same path as those medieval scholars participants in a citizen science project spanning 1,000 years. But perhaps the map's most stirring message is for the dreamers, those who look up and see not just points of light but possibilities. Its spirals and symbols, so eerily resonant with modern cosmology, suggest that intuition can sometimes outpace equations, that the human mind has an uncanny knack for glimpsing truths it can't yet prove. In an era where algorithms pass the universe, the map champions the role of imagination, of daring to sketch the unseen forces shaping reality, even when the tools to confirm them lie centuries ahead. Ultimately, the Samarkand Map is less about the past than the future. It asks us what mysteries we might solve if we commit to observing as diligently as its creators did, what patterns might emerge if we devote lifetimes to watching rather than scrolling. Its true legacy isn't in the stars it plotted, but in the timeless human impulse it represents, to reach beyond our grasp, to leave maps for those who'll come after, and to find our place in a story written across the sky. From ancient eyes to modern screens, this map bridges centuries, not just as a relic, but as a living testament to humanity's shared gaze skyward. Its parchment, fragile yet enduring, carries more than star positions. It holds the fingerprints of countless seekers who dared to chart the infinite with nothing but patience and curiosity. The real magic lies not in its predictions, but in its proof that cosmic understanding transcends technology. Those medieval astronomers, squinting at the heavens through desert dust, grasped truths we now confirm with satellites, not because they had secret knowledge, but because they trusted the most powerful tool of all, time. Generations of observations, meticulously recorded and refined, became their telescope. What does this mean for us today, scrolling through digital star charts on pocket-sized screens? The map's legacy is a clarion call to reconnect with the sky's tangible wonders. Modern astronomy may peer deeper into space, but we risk losing something vital, the intimate, awe-filled relationship our ancestors had with the night. Their maps weren't just functional. They wove science with storytelling, mathematics with mythology, reminding us that the cosmos isn't just equations, but our oldest mirror. Every constellation they named, every celestial event they tracked, was a dialogue between humanity and the universe. This parchment also shatters the myth of linear progress. We assume newer means better, but the map whispers otherwise. That brilliance isn't bound by era. Its creators achieved feats modern software would struggle to replicate without historical data, proving that insight flourishes wherever curiosity is given room to breathe. Their work invites us to question what else might be hiding in plain sight, waiting for fresh eyes to see it. Could today's overlooked patterns hold keys to tomorrow's breakthroughs? The map suggests an answer. Sometimes the future belongs to those who study the past. As we stand on the precipice of new cosmic discoveries, from gravitational wave astronomy to exoplanet atmospheres, the map's greatest lesson is humility. It reminds us that every generation believes it's finally unlocking the universe's secrets, only for the next to reveal how much remains unseen. Those medieval scholars didn't have all the answers, and neither do we. But like them, we get to keep asking, keep mapping, and keep passing the torch. So the next time you step outside under a starry sky, try this: put away your phone. Trace the Big Dipper with your finger as they did. Imagine adding your observations to a parchment that might one day inspire centuries hence. Because the universe isn't just something we explore, it's a story we co-author across time. If this journey through the stars resonated with you, join the conversation below. What mysteries do you think our descendants will uncover from the maps we're making today? Don't forget to like, subscribe, and together, let's keep looking up. The cosmos has never stopped calling. We just